Hi folks, a bit of a shorter lecture today because it's a short section. We're looking at section 4.2 in Herstein, which has some lemmas regarding properties of rings, basic properties of rings, now that we've defined them and seen a number of examples. Okay, so without further ado, I just wanted to make a couple of corrections or additions. I think I forgot to define zero divisors in last class. And we'll do that now. A zero divisor is an element A in R, where R is our ring, such that there exists B in R with AB equals 0. And we saw an example of this. Our example for a ring with zero divisors, or one of our examples, was Z6, the ring of integers modulo 6. In this ring, the class of 2 times the class of 3 is equal to 0. Okay, and so both of these are called zero divisors. And strictly speaking, A is a left zero divisor if AB equals 0. But in a lot of contexts, we're working on a commutative ring anyway, so it'll be both a left and a right zero divisor. Another note is that integral domains are commutative rings with no zero divisors. Excuse me. So this is also, I'm not sure I made this condition clear in class, that it's only considered an integral domain if it's also commutative. Okay, so now let's work out some of the lemmas about rings. So again, we're assuming R is a ring, so let R be a ring. 0 is the additive identity. And A is just any element in R. So our claim is which we want to prove right now is that A times 0 equals 0 times A equals 0. Okay, well, let's play around with this a bit. We know that 0 is the additive identity, so if you add 0 to anything, it's the same. So in particular, if I add 0 to itself, it's the same. Well, this means that this is equal to A0 plus A0, but we just saw up here, but we know that this is also equal to A0 because 0 is equal to itself. So canceling or subtracting on both sides of the equation tells me that A0 equals 0. By the same token, 0A equals 0 plus 0A, which is equal to 0A plus 0A. Okay. Obviously, it's a group under the operation of addition, just as up here, so we can subtract 0A on the left from both sides, which gives us that 0A equals 0. And then clearly, since they're both equal to 0, they are both equal to each other. Okay, so this is nice, just as we were accustomed to in the ring of integers and other rings we're familiar with. Multiplying by 0 gives you 0. And that's not using anything we know about 0 except that it's the additive identity. Okay, here's another one. Now we have R is a ring. A and B are in R. And we're going to claim that A times minus B equals minus A times B equals minus AB. Okay, and here we're going to use the fact that the minus operation defines the additive inverse, and that's all we're going to use. So, and I should have made it more clear here why I can do this. This is a result of the distributive law. Okay, and that's one of the axioms of rings, and so that's where it comes into play here. This is also a distributive law. Remember, there's a distributive law on the left and on the right. Okay. So we know that A times B plus minus B, by definition of the additive inverse, this is equal to A0, right? We just learned that this is equal to 0. So using the distributive property, this is equal to AB plus A times minus B. But the fact that AB plus A times minus B equals 0 means that A times minus B must be the additive identity of AB. Okay? Since it's additive identity. It satisfies the property of the additive inverse, I should say. Okay? And by the same token, you can do this on the left with A plus minus A. So A plus minus A times B equals 0B, which is 0. But this is also equal by the distributive property to AB plus minus AB. So by the same token, minus AB equals the additive inverse of minus of AB. Okay? So we've proven that minus also works the way we would want it to work, that we can kind of just pull it out to the front, that we don't have to worry about products of additive inverses not canceling the way we would, not behaving the way we would expect them to based on the classical example of the integers. Okay, here's another lemma. We have our ring. And we have A and B and R. Now this says that minus A times minus B equals AB. Okay, so to get to this, we'll probably use the same strategy that we've been using all along. So let's take something like A plus minus A times B plus minus B. Is that necessary? Yeah, let's do it this way. Let's see what happens. If we have to start over, we'll start over. So we get, using the distributive law, we get A B plus minus B plus minus A B plus minus B, and that in turn equals AB plus A minus B, which we know is the same as minus AB, plus, based on the last slide, plus minus AB plus minus A minus B. Okay, now we know that these two things cancel. Okay, so we're left with minus AB plus minus A minus B. On the other hand, we know that what we started out with up here was 0 times 0. So this has to be equal to 0 times 0, which is obviously 0. So if minus AB plus something is 0, that means that minus A times minus B equals AB, which is the additive inverse of minus AB. Okay. Okay, assuming we have a unit in our ring, then minus 1 times a equals minus a. Okay, this is a straightforward consequence of what we just proved, right? You just take, we just proved that minus a times b equals minus ab. So just take a equals 1 and b equals a. Not this a, but the symbol a in this last equation. And what we get is minus 1 times a equals minus 1 times a, but that's obviously because it's just the multiplicative identity that gives me minus a. Okay? That's straightforward. Okay, so here's a variation on the typical formula for a square, a square of a sum. So if we have a plus b squared, that's going to be equal to a squared plus b squared plus ab plus ba. Okay. The only difference between the standard is that sometimes this will be turned into 2ab, but that's only if the ring is commutative. Okay, that's not true for rings in general. So let's prove this. And we did something similar a couple slides ago. We're just going to use the distributive law twice. So we'll get a times a plus b times a plus b. So that's splitting up the sum on the left using the distributive law. Then you get a squared plus ab plus ba plus b squared, just by distributing. And that's easily equal to a squared plus b squared plus ab plus ba by the commutativity of addition. So the fact that plus commutes. Okay, pretty straightforward. Okay, now we'll make a definition. A Boolean ring is a ring satisfying x squared equals x for all x in R. Okay, so whatever element, when I multiply it by itself, I get the ring, I get the element back. Okay, so multiplication behaves in kind of a funny way. Okay, so we have x squared equals x, and now the lemma 6, claims that a Boolean ring is commutative. And this is a bit fun to prove. So we have to prove, in order to show that a ring is commutative, we want to show that xy equals yx. Okay, this is what we want to show for any xy in R. Okay? Well, if we want xy to show xy is equal to yx, we have to, this is obviously not true in general, so we have to use this Boolean property. So let's start by adding the x and y together and then squaring it and see what happens. So on the last slide we saw that this is equal to x squared plus y squared plus xy plus yx. On the other hand, we know that in a Boolean ring, whatever you square, you get back the element itself. So we should just get x plus y. Okay, by the same token, this is equal to x, because x squared is x. This is equal to y. And we have xy plus yx. Let's make a new slide on the next page. Oops. Okay. So this is what we have so far. So if x plus y equals x plus y plus xy plus yx, well, we can get rid of x and y because we can add their additive inverses. You know, we always have additive inverses because it's a Boolean group under addition. So we get 0 on the left-hand side is equal to xy plus yx. Okay? So this is interesting. So we're going to use the fact this is equal to 0 to multiply things on both sides, and the left-hand side will still be 0, but the right-hand side will end up changing. So let's multiply on the left by x. So x0 will be equal to 0, obviously. And on the right-hand side, we'll get x times xy plus yx. Okay, well, that gives us x squared y plus xyx. Okay. And here, x squared is plainly equal to x by Boolean property. So we have xy plus xyx. Okay. What if we multiply on the right? So we get 0x, but that's equal to 0 as above. And the expression we get here is xy plus yx times x equals xyx plus yx squared. And this is equal to xyx plus yx, since x squared is equal to x. So, because both of these are equal to 0, we have that xy plus xyx equals xyx plus yx. Okay, recalling that the addition is commutative, we can add the additive inverse of xyx to both sides to get xy equals yx. Okay. So this is pretty interesting. It's also pretty interesting keeping in mind that up here we had that xy plus yx equals 0. So another consequence of this for any xy in the ring, xy plus xy equals 0. Okay? And in particular, if you have a unit, so if 1 is in R, this would imply that x plus x equals 0 for any x in R. Okay? So this is a very special ring with a lot of special properties, and we'll perhaps see some more of them as examples going forward in the course. Okay, as I said, it's a short lecture today, but we'll talk more about rings next week. Take care.